Very good, thank you. Thank you and welcome back for the second installment. So I was just going to remind you what we did last time, and I'll tell you what I'm planning to do this time. So I think last time I really introduced the cohomology of BG, and in particular, I introduced this construction for EG as a product of infinite spheres. So that's something that is going to come back in various forms. And then there was the theorem of Benson and Carlson that I described, but I'll restate that later. So I'm going to carry on going. I mean, I've taken a different approach to the other speakers. I've started by spotting patterns, and we're going to move towards structural statements, but we'll probably not get to the structural statements today. We'll just get to more patterns. Well, you judge me at the end whether this works or not. Okay, so one of the things that I wanted to really talk about today is the local cohomology theorem. So Srikanth has now introduced us to local cohomology, and I want to say that again because I want to take a slightly different point of view, because I'm going to sneak in some techniques which are going to apply in more general contexts later. So this is the same definition. Well, no, let's have a ring. So my ring's probably going to end up being a graded ring most of the time, but this is a graded ring. So you might like to think it's the cohomology of BG, for example. And then we're going to have an ideal generated by some elements. And then I just want to define the I-local cohomology. So Srikanth defined that as the right derived functors of the torsion functor. I don't want to do that because it doesn't always apply in my context. So instead, so Srikanth did make this definition. He said we can take the cochain complex for this sequence of elements, so my generators, and then I could just take a tensor product of the ones for each factor. And then if I've just got one factor, I could write it as very simply as R and R with X inverted. So he did all that. I'd just like to observe this is also the fiber of the map of chain complexes from R to R of 1 over X. So this here is a cochain complex with stuff in degree 0, and degree, homological degree -1, but it's the fiber of a map from R to R1 over X. Okay, and then the local cohomology. I'm going to define it not as right derived functors, but as the cohomology of this explicit complex. Well, that's my definition, and well, Srikanth gave the theorem that that's the same, so that should be okay. I'm just going to now list a few properties, and the point of listing them is to say that they're elementary, or many of them are elementary to prove for things defined this way. The first one we can, Srikanth gave the proof of this. So it's the kernel of the map from M to the sum of things with the elements inverted. So of course it'll be the I power torsion. Then I wanted to say that this is I power torsion. Any element is killed by some power of I. And then I wanted to say that K infinity I itself as a complex only depends on the radical of the ideal I. So again, that was something Srikant said, but the point is we can have, I mean, it's probably just worth seeing how simple the proof is. For I power torsion, all I've got to do is, of course, if I take one of these terms, if I invert x, then I get the identity. So if I invert one of the generators, it's acyclic. So inverting one of the generators makes it acyclic, but then if I invert a sum of several of them and take a power of it, the power will be divisible by some power of an element for a general element of I can write, what are we going to call that? Y is just a sum of the x's, and a suitable power will be divisible by one of a large power of the x's. The power is divisible by some xi to some large power. So I pick the power that I need to annihilate my element, and then I choose my power of y, and so that it's divisible by such things. Oh, right. So I have now proved, firstly, that it's I power torsion, and secondly, I suppose I haven't quite proved. I've proved that if I added some additional elements, additional generators to this list, I would get if I added y, then I wouldn't make any difference. So this is equivalent. So adding extra generators doesn't make any difference, and obviously replacing my powers doesn't make any difference. So. Okay. So we will use these sort of elementary facts later. Then the next thing, which is probably very well known to everyone in the audience, but probably needs stating, is that if I look at the local cohomology, the first non-vanishing one is the I depth. First non-vanishing, starting from the bottom. Is the I depth, the length of the longest sequence from I, longest regular sequence from I on M. And then I guess, I mean, that's not quite so elementary, but it's in lots of books on commutative algebra. Then, just to connect into what Srikant said, if I take local cohomology as I've defined it, if R is going to be Noetherian. If R is Noetherian, then, and M is injective, that's not hard to prove, and so of course, and in that case it's gamma I of M. And so it's suitable for calculating right-derived functors, and so this is just the set of right-derived functors of M. So Srikant defined local cohomology using this side and made it a theorem that it could be calculated this way. But now we're speaking the same language. Okay. Oh, and then the last fact is that it vanishes above the Krull dimension. Again, I'm sure I I guess this is due to Grothendieck, of course, but this is HI equals 0 for I greater than the Grothendieck of R. So this is due to Grothendieck and Tohoku. You just prove it by a sort of induction. Okay. So that's the background. I just want a couple more examples. Maybe the very first example would be this is to get you used to having a graded ring. So I'm going to have K of X, and my generator is going to be of degree D. So what is local cohomology with respect to X? So I take K of X, which I draw a picture of, and I invert X. And I take cohomology. So in this case, inverting X is an injective map. So H0 is 0. And of course, you can see it isn't surjective. And that's H1. And so now you can see the duality. That's the same with K as X was, but now it's upside down and there's a shift. So 1x, K of X. Vector space dual. So that what is this? What are the degrees? This is degree 0, D, 2D. This is degree minus D. So once I dualize, I get up to degree D. So this is okay. And I'm going to do, well, let's have one more one-dimensional example. Since I mentioned it last time, this was the ring of x cubed and x to the 5th inside polynomial on one generator. I drew it again here. It won't feature again, but I just wanted to mention it. So now, what ideal shall I choose? I can choose the maximal ideal, but we know that it only depends on things up to radicals, so I might as well take x to the 8th, say. And then once I've inverted that, what happens? So here is a picture of R. Once I've inverted, I get everything above degree 8. So once I've inverted it, I get everything. I beg your pardon, like another color. Okay. What's your favorite color? Okay. This is the ring generated by x cubed and x to the 5th. It's your exercise in your notes to fill in that subring. If you can't see this, I'm sorry at the back. But the point is that above x to the 8th, everything is included. All powers of x are included. And so once I invert x to the 8th, I get all powers of x. Maybe I will stick to yellow. And so again, the local cohomology, x to the 8th is a regular element, so it's still injective. So H0 is again 0. And H1, well, that was the thing I drew last time. I drew it in a different color, and it was not very visible yesterday either. But over here, I have the things which are not included. This is x to the 7th. It's not in the image. x to the fourth is not in the image. X and x squared are not in the image. And then, of course, nothing in negative degree is in the image. So once again, as I said last time, if you turned R upside down, it becomes red stuff, but now we've got this in a, so H1, x to the eighth, R. And if I dualize, well, we have to think about the top thing in H1 is the seventh power in degree 7. So once I dualize it, it's in degree -7. So, anyway, that's just another example of a random ring with this nice duality property, which we'll very soon declare as the Gorenstein property. Okay, one more example we really need is the polynomial ring. So in some sense, the message of this first part of the talk is that everything came from products of spheres, everything comes from polynomial rings. You know, it depends whether you're a topologist or an algebraist. So I'm just going to do the case with two variables, k of x, y, maybe degrees d and e, and the ideal generated by x and y. And so what does the stable Kossel complex look like? I'm going to choose these generators. I'm going to draw you a picture in a moment. And this is the main trick of this this lecture. So pay attention here. Here we are. So I'm going to draw powers of x along the x-axis, powers of y along the y-axis. And so that's a picture of k of x, y. And I'll mark the origin in blue. That's 1. This is of course x. This is of course x squared. This is y. This is xy. So I've got a basis of monomials which I'm marking at the intersection points, and then I'm going to invert y, so I get the whole right-hand plane. I mark in again the origin. And then I invert x, so I get the upper half space. Mark the origin. And then I invert x and y, so I get the whole plane. And I mark the origin like that. So then, I mean, you have to put in some signs to make it work out. I guess. I guess I'll put the sign here, but assume k is a characteristic 2, then you don't need to worry about signs. Okay, so to calculate the local cohomology, we don't need to do any algebra. We only need to do set theory. I'm going to pick a vertex in the positive, the positive quadrant, this quadrant. I can pick any one, but let's pick that one. And that occurs here. It occurs here, and it occurs here. So I get 1, 2, 1. It's an exact sequence. So there's no cohomology. Pick something. So no cohomology in the first quadrant. Second quadrant, Second quadrant, there's nothing here. There's nothing here. But there's something in the second quadrant here. Let's go over here. And that occurs here. Okay, so now I've got 0 goes to one-dimensional, goes to one-dimensional. It's another exact sequence. No cohomology in the second quadrant. And similarly, the fourth quadrant. However, you now observe that in the third quadrant, I have nothing, 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 and then I have this. And so you can see this is a copy of the thing you first thought of, and you can see what the top degree is in. Top degree is in degree minus d minus e, because what is this top element here? This top element is 1 over xy. Okay, so the conclusion of this calculation is that hi xy kxy. Well, I'm going to tell you what its dual is 0 if I is not equal to 2. And if I is equal to 2, I'm supposed to get the d plus e suspension of the ring I first thought of, which is k of xy. Okay, so this will be very familiar to many of you. I'm just going to do one. I don't need to give details here, but you can see the same argument will apply for a general one. We want to say that. Oh, is there a question? I just want to do one more example, which is a polynomial ring I'll call P on, let's have R variables, x1 up to xr of degrees d1 up to dr. And I'm going to let d to be the sum of those di's. And you can just see the same argument's going to work. Hi maximal ideal or P check is going to be 0 if I is not equal to R, and it's going to be sigma d P y equals R. Okay. Right. So that was probably a recollection of easy stuff. Now I can define Cohen-Macaulay and Gorenstein, which are, in a way, I'm going to do the same sort of thing I did here. I'm going to do it in a way that applies more generally. So I'm going to try write it here. Well, Cohen-Macaulay, I suppose, won't, but let's try it anyway. So definition. So, well, the point is that now we know that Cohen-Macaulay-ness is detected in local cohomology. So R is Cohen-Macaulay. So R is now a local ring. If it has a regular sequence of length equal to the dimension. The cruel dimension, that is. And in other words, i.e. the local cohomology with respect to the maximal ideal of the module itself is 0 for I less than this cruel dimension. Okay, so that Cohen-Macaulay-ness is detected in local cohomology. And then so we have had the definition of Gorenstein, but we're going to have it again. So let's stick with a local ring. So the definition we've had before, the official definition is R is Gorenstein if it's got finite injective dimension as a module over itself. if the injective dimension of R is finite. But then as a matter of commutative algebra, that has some consequences. And then, well, obviously if it's a finite injective dimension, when I calculate X groups, there are only going to be finitely many, but in fact, there is only one, and it's equal to the Krull dimension, which I'll probably start. I'm going to let that be R, so it's only the rth one. And furthermore, in that degree, it's also determined by this, and it's a copy of K. Now, normally I just say it's a copy of K, but I want to remind you we've got graded rings. And so I think, it's certainly a suspension of K, a shift of K and some amount, and I'm going to make it A plus R. So don't worry about suspensions. I went to bed several hours later as a result of trying to get the dimensions right. I hope I've done so, but if I haven't, we'll discuss it later. Okay. You don't like that? No. Sorry. Yes, for some A. Some integer A, and which hasn't been, you're absolutely right to say, I should have said R is Gorenstein of shift A. Now that we did have Iwinaga-Gorenstein, and there was another meaning there. The word shift wasn't used, but there was another thing. It was more like R, I think. But anyway, I'll call this shift A. Okay, and then I suppose I need to say, in commutative algebra, there's a third characterization, but I'm going to call that separately. So see, R has Gorenstein duality. Of shift A. If it's Cohen-Macaulay and if it's Cohen-Macaulay, so there's only one local cohomology group, which is the top one. And well, I suppose I've done everything else in terms of, well, okay, I'll do this in these terms. I get the same A plus R. So if I wanted to get it in the those terms, I would talk about the dual on the other side, but it doesn't. Well, yeah. I'm going to carry on assuming that R is a polynomial ring. R is graded connected. So it's going to have K in degree 0, and it'll be finite dimensional in each degree. So taking duals is not going to matter. So that applies to the cohomology of BG. Yeah, so this is, so here assume R is K in degree 0 and finite dimensional in other degrees, in each degree. So then I can take vector space duals, and I don't need to discuss MATLIS duality in great detail. Okay, so we've got some examples up here. So this is this first example, polynomial on one generator of degree D. This is a Gorenstein. From this calculation, of shift -1 minus d. And this one is Gorenstein of, well, actually, let's just do the general case. This is Gorenstein of shift minus R minus D. Okay, well, if you like, that's just telling me your grading conventions. No, sorry, it's telling you my grading conventions. Okay. This is just a shift, so I can write it in a formula in a second, but if I take the nth suspension, I get the same thing, but it's shifted up in degrees by n. So sigma n for a graded module m in degree I is m in degree I minus m. So I think, I mean, that's something that has come up in several other talks, and I think there's I mean, it is necessary to make this definition, so I tell you I'm doing homological degrees, so that I'm not sure if Sudesh would agree with this convention, but anyway, that's the convention that I will be using. Okay, so now I can restate the local cohomology theorem, and I'm going to prove it. So, theorem for any finite group G, so without condition, I mean, yeah, there is a spectral sequence which begins with the local cohomology with respect to the maximal ideal of positive degree elements of the cohomology ring of G, and which converges to the homology Bg, which you notice is the dual of the cohomology Bg. So, oh yes, consequently, so hence, if the cohomology of Bg is Cohen-Macaulay, then, well, the spectral sequence has only got one column, local cohomology column. So this will say that HRM of the cohomology of Bg is equal up to this R-fold suspension, and we're going to have a little conversation about the suspension in a moment, plus or minus R of this, which is the dual. So, in fact, there's a slight change from last lecture. In last lecture, I didn't emphasize the fact that this is co-homologically graded. My conventions so far today have been homologically graded. That's just fine, but that means I've got to be consistent. So if I did, and how are we consistent? Well, look at the case of G is cyclic order 2. So the cohomology of Bg was polynomial, and K is characteristic 2. K except F2. This was polynomial on a single generator X. It's a cohomological degree 1, which is a homological degree -1. So that's the little conversation we've got to have. And so when you take the local cohomology, you have to look at this picture the other way up to see what happens, and this is a plus R. So anyway, don't worry too much about the degrees. You can get them right if you think hard enough about it, and hence, if it's and hence, the Hilbert series f of 1 over t satisfies minus t to the r times f of t. So t here is of cohomological degree 1, just as it was before. So it's no change. I defined the Hilbert series before in the same definition. Okay. So I want to, I mean, where R is the Krull dimension, which, as you say, is the P rank, yeah. So the fact that R is the Krull dimension is sort of going to fall out, but then the fact that it's that Krull dimension is the rank is a big theorem. Okay. So I'm planning to prove this result, and I'll prove that M is the maximal ideal, which is all positive degree elements. Yeah. Yeah, so cohomology of BG is in cohomological degrees 0, 1, 2, 3, and so forth. And so its maximal ideal is everything in cohomological degrees bigger than 0. So I should write that. Yeah. And cohomology of BG, as I mentioned yesterday, is, by theorem of Quillen and Venkov, Noetherian. Okay. So here's the proof. Actually, here's the proof. These pictures are the proof, but I have to explain why. You remember when we had a group acting freely of a product of spheres, a sort of generalized torus, we made EG by taking infinite spheres. So we're going to do the same thing in algebra. So I'm going to assume for now there is a free resolution of K over Kg of the form which is it's a product of a certain number of factors, which might not be R. So let's make it N, and these are products over tensor products over K, where the EI are periodic. EI is a periodic complex, which I'm going to draw a picture of. It's going to have a piece here, which as a topologist I'd like to think of as a sphere. So that piece there, it's inside here, we've got a little chain complex. I'm just representing as a box. And the homology of this is the homology of a sphere. So it's got K in degree 0, and it's got K at the top. And so I'm going to make a periodic complex by repeating this. And of course, I have to shift it along in order to do that. And the splicing is easy because the homology of SI was just supposed to be K at the top and the bottom. So I had a name for that. I suppose the top is probably if S equals 0 or well, it doesn't matter, but I'll call it pi I minus 1, 0 otherwise. Okay, and this is EI. This whole thing is EI. EI starts here with the bottom piece in degree 0. This is in degree pi I. This is in degree 2 pi I. This is in 3 pi I. And so forth. So that's what EI looks like. So it's a periodic complex, but it is not a complex of 3 modules. But when I tensor product them together, it is. Okay. So maybe I should have just illustrated that by saying this is the, if I add a k at the top and the bottom, it's exact. Okay. So now let's suppose we've got that. And of course, I'm going to take the tensor product of, say I took the tensor product of 2 of those, I would have something which looks very much like this picture. I'd have E1 in this direction and E2 in this direction. I get a double complex. And then I could also form this picture by, in the E2 direction, carrying on the periodicity into negative degrees. And in this picture, I take the E1 direction, copy it into negative degrees. And here I do both. Okay, so that's what we're going to do. And then the proof is by considering 2 spectral sequences which arise from this. Okay, so let L of A, so it's like the stable costal complex, except it isn't yet because I've got to dualize. So instead of using K, I'm using L. So this is what you get by stacking boxes. A is a subset of 1 up to n. Stack boxes allowing negatives in the I direction if I is in A. So I will just draw you a couple of examples, and that will, I think, make it sufficiently clear. So if n equals 1, I've got, well, here's E1. So that is L of the empty set. I'm not allowing negatives in any direction. And there is only one direction to allow negatives in, the L of 1. And those have also got okay, so they've got L of the empty set and L of 1, and of course there is a map of chain complexes upwards. And so I've got a double complex in this case, which is going to be called probably L. So L, make these into I'll just say double complex L. And this is the whole thing. I'll do one more example, and I won't trouble with the notation in general. It stops here. This is degree 0, which has been blue. Oh, L of the empty set is not permitted negatives in any direction because A is empty. to the right. Oh, that goes on infinitely far in that direction. This is E of I, yeah. And there's zeros over here, which I won't write. I will just draw the two-dimensional one and then try and use it. So the two-dimensional one, probably for reasons of space. Oh, well, I could try doing, well, how about this? I'm going to reuse this diagram. This is L of the empty set now. And look, instead of, previously these were just copies of K, vector space K for each point. But now each little interval is a copy of this S of 1 in this direction and S of 2 in this direction, but they're stacked in boxes that way. Here, I was permitted, this is bound to cause confusion, isn't it? Let me not take this, okay. Here is L of the empty set, but the arrows are going, oh, it's a double complex, isn't it? So. Then I'm going to have L in the one direction. I'm allowed in the one direction to have negatives. But not in the zero direction. Sorry, not in the two direction. And then L of 2. L of 2, I'm allowed to go negative in the down direction. And with similar convention about blue dots, these are blue dot at the origin. Oops. Well, it doesn't matter where it is it? Sorry. Say. And then L of 1, 2. I stack boxes everywhere. And well, the way that the arrows go, I mean, I have vertical maps going up. Okay, so you're supposed to get at least some idea of this pattern. And now I can tell you the rest of the proof. I'm going to take HOMs of this complex into K. Now take HOM over Kg, this multiple complex L into K, and take cohomology. Okay, so it's a double complex. Within each, I don't think about the n different directions in each entry. I just think of each just being a single complex, and then there's the costal direction vertically in that picture. So if I take cohomology in the L direction, what happens? If I take cohomology in the L direction, I get exactly the argument I showed you over here. It was just an argument with set theory, which just said that it's exact except in the third quadrant. So how does that work out? So two spectral sequences. So depending on whether we using the L filtration or L direction and chain complex direction. So if we do the L direction first, what do I get? Well, I get the cohomology of hom kg of, well, it's the homology of L dot into K. And by that argument, the only thing that's left is a copy of the dual of E. So this is sigma minus n E, where E is the tensor product of the, E is this tensor product that we had. And that's the rule for calculating group cohomology. Sorry, it's the rule for E check, sorry. It's the rule for calculating group homology. Up to suspension, and I'm not going to, that's the least of our worries at the moment. Well, it's probably minus n, plus or minus n. Okay, so the spectral sequence in that direction collapses. But if I calculate the cohomology direction first, let's just think what happens when I form, let's look at this case, when I form L of 1 from L of 0. I took an inverse limit of truncations like this. So when I take the duals, I get a direct limit construction where each of the maps in the direct limit is multiplication by the group cohomology element represented by the sphere complex. So you get the cohomology of the costal complex, the stable costal complex for, let's call it zeta 1, zeta 2, up to zeta n. Which is the local cohomology for zeta 1, zeta n, cohomology ring. Where S1, where SI, oh, here it is, here's SI, where SI represents the cohomology class zeta I. Now, what SI is, according to this, it's an extension of K by K of length pi I plus 1, and it represents a cohomology class, which I'm calling zeta I. Okay, so that's a sketch proof of this. And so the point about this sketch proof is all we needed to do was think about stacking boxes. We needed to think about set theory, products of spheres, and so forth. How do I get? Oh, very good. So I said this was an assumption. Let's discuss that assumption. That's exactly what we need to do next. So I'm going to give you several methods. Actually, I already gave you one yesterday, which was to use these products of spheres. Okay, so the assumption. So method one, I call it method one, yes. Let's suppose we're in a case when EG is a product of infinite spheres. So we know that isn't everything, but we know it does include all p groups, all nilpotent groups. So it's a pretty big class. So in that case, SI is the chain complex of VI, the sphere for VI. And well, so that will be a complex of modules which won't be free if VI has some fixed points. But the product was free. Okay, so that method one, so this covers all nilpotent groups. Okay, but it doesn't cover everything. So method two is due to Benson and Carlson. Which is to reverse the last bit I did, which is to say, I look at the cohomology ring, its polynomial over its subring. Okay, so cohomology of BG by Noether normalization. Cohomology of BG is finite over some polynomial subring, K of zeta 1 up to, well, actually zeta R. We didn't know that just now, but we do in this case. R is the cool dimension now. And I just use SI to represent zeta I. And of course, that would be a complex, well, you can arrange it so that all the terms are free modules except for the last. So where, and take SI to represent zeta I. So, you know, I mean, one way to do that is you take a free resolution of K over Kg and then just truncate it appropriately using, you imagine you've got the whole thing. This goes on forever. I suppose this is pi I minus 1 or something. It carries on, and we just represent it with a map from p pi I. So this is zeta I goes down to k, and then you take the push out, and then keep the rest of these terms. So this will be a construction. This is a construction which will be familiar to some of you, and my exposition is too quick to really communicate it, but it's a routine construction to represent zeta I. Okay, and then you find that the support of SI, you know, so then support of SI, well, in a sense which is more general than the one Srikanth described, but you know, in exactly in the same spirit. So this is supposed to be B of zeta I inside spec of the cohomology ring. And because the cohomology of BG was finite over this, over this polynomial subring, the intersections of the VIs are empty. And then one of the things that is analogous to a property of the support Srikanth talked about is that means, hence, the tensor product of these SIs is free. There's R of them now, is free. Over Kg. Oh, projective at least, but projective. kg. And so that's enough to get you going. You have a free resolution of the stated sort. Okay. I wanted. I was going to really show you that you can deduce this statement about Hilbert series from the local cohomology theorem. So maybe I'll try and do that. So I'm going to use this same proof to prove another theorem in just a moment, but here we go. This is where I need to get my suspensions right. Okay, so remember we're in the context now. We've got, let's suppose, R is the cohomology ring of BG, and by the theorem and its Cohen-Macaulay. So by the local cohomology theorem, that says that the top local cohomology is the minus R. Well, we can just, I'll take duals here. I take the dual of local cohomology theorem, so I keep on talking about Noetherian modules. And then this is going to be sigma minus R. So that was what we got from the local cohomology theorem. So now let's, because R is Cohen-Macaulay, so by the Auslander-Buchsbaum formula, it's actually free as a module over a polynomial subring. So R is P tensor F, where F is a finite complex, finite graded vector space. So where F is finite dimensional vector space. Okay, so now I think we're all set up. So R is the suspension I've now moved this over to the other side, sigma R H R R M check. The suspension is unchanged. Now, if I calculate the local cohomology with respect to M, that's the same as if I calculated the local cohomology of R as a P module. And then I would get HR MP of P check F check. So I've used the fact local cohomology can be calculated with respect to a ring over which it's finite. Okay.
So
and
is P the generators of P in degree 1, or is it? It could possibly have higher degree.
I can't hear what you said.
Are the degrees of the generators of P 1, or could that be?
So let's actually,
not necessarily 1. Huh?
Let's say they are exactly as they are miles over there on the other side of the board. Maybe they're x1 up to xr of degree d1 up to dr. I did this calculation earlier, and because of that, we know the answer. We know that the local cohomology of P, and I did it with the dual, I think, this was sigma d P. Hope I remember. I didn't. I rubbed it out. Okay. So that was our conclusion.
Yeah, that is okay. But I am just slightly confused about the second line to the left of what you've written, where you've written HRM of it star BG check is, yeah, the shift above sigma. Shouldn't that involve the D's also, not just R? Or shouldn't that be A plus R? I mean, minus A of A.
I mean, so in our case, A equals 0. And the question of whether it's plus or minus R, this is about whether we're talking about degrees or co-degrees.
Yeah.
And everything here is degrees. And I do hope I've got it right.
Okay, thank you.
Okay, so we've got that far. So now I'm going to take Hilbert series, and I'm going to have the convention that if I'm going to put square brackets around M of T, which will just be the sum dimension over K of MS T to the S. So let's hope this works out. So here we go. Square brackets R of T. So just from the equation on the previous line is, you're quite right. Oh no, so far so good, but there's another step which and then this whole thing is sigma R minus D of P F check tensor. There's a tensor in there if you like. Okay, so now I'm going to take Hilbert series associated to that. This is R of T, and that's T to the D minus R. As you remember, T was of degree -1. P of T F of 1 over T. And now P of T, we worked out this is T to the D minus R, -1 to the R, T to the minus D, P of 1 over T, because that's the other thing we checked last time. We found what P of 1 over T was precisely -1 to the R times T to the D times P of T, and then an F of 1 over T. And happily, my T to the D and T to the minus D cancel out. I get minus T to the R, square brackets R of 1 over T. So this is not a test of whether I got the arithmetic right. It's just to show the method. The method, once you know the spectral sequence collapses, you can make a Hilbert series calculation. And there's an ingredient from the Auslander-Buchsbaum formula. Okay. You can imagine doing it, the two-step thing is a little more complicated, but it's the same idea. Okay, I just want to mention another thing you can prove by the same method, and I think I won't, I'll just say it. Same method. So one reason for doing this is I'm going to spend the rest of my lectures giving you an entirely different method for proving that cochains BG is Gorenstein and getting a local cohomology theorem. So I didn't need to do this for that, but this other thing I don't know how to do by another method. So same method gives following theorem due to myself and Bob Brunner, which says that, of course, this won't appeal to everyone, but if A is a finite dimensional sub-Hopf algebra of the C-knot algebra, well, these are classified but you know, there are lots of them anyway. And it's of formal dimension. It's a finite dimensional Hopf algebra, so it's got a formal dimension. It looks like it is a Poincaré duality algebra, if you forget structure, of formal dimension F. Then there is a local cohomology theorem. Then there is a spectral sequence, which, well, so I'm now my finite dimensional subalgebra of the C0 algebra is graded, so its cohomology will be bigraded. But it's bigraded and it still has a maximal ideal of positive bi-degree elements. So M is H greater than 0, if you like. So you can still calculate its local cohomology and get a spectral sequence. So I mean, there's only one real example interesting example you can do by hand. You can do exterior algebras on some generators easily by hand, and then it doesn't tell you very much interesting because those are exterior algebras, so their cohomology is a polynomial algebra, and we know that this, we know that the cohomology of a polynomial, local cohomology of a polynomial algebra is a dual of the thing you first thought of, so we know it there. So the first interesting example is maybe the algebra A is A of 1. So this is an exercise for you. If A is A of 1, it's the thing generated by square 1 and square 2, which looks a little bit like this. It's of formal dimension 6. There it is. And the cohomology of this is also well known, and those of you who know it well will recognize the picture, and I won't explain more. So it's like this, but then made periodic with oops. So the exercise for you is to I mean, the maximal ideal is sort of generated by this element H, and this element, I don't know what its standard name is, let's call it B, and then you go to a little local cohomology calculation to let you check out that, and F equals 6, which you can see from the picture. 1, 2, 3, 4, 5, 6. Okay. Very good. So I think that's the end of this particular approach to the duality theorem. I'd like to make a start on the next topic, but I don't know whether. Yes, I think perhaps I'm going to I'm just going to begin.
So I
mean, are the questions? Sorry, that was what I was hesitating about. No. Are the questions on what I've done?
Yeah, no, I was about to say it's 12:30.
Oh, is it time to stop?
Yeah.
Oh, it's perfect timing. Okay, then, thank you.
Okay, so let's stand this.
Thank you. Yes, for compact Lie groups, you have to have a hypothesis. So let me. There's a spectral sequence. Yeah, that's worth saying. So there is. Okay, so for in general, there's a suspension you need to put in here. So if you've got a compact Lie group, the suspension is by the dimension of G. By the dimension of G, yes. This is if E is compact Lie, but it doesn't always work, provided the group of components of G acts trivially on the adjoint representation, provided add G is orientable over K. So if you didn't like that, you can instead do the homology of BG to the add, and then you don't need to. So if you didn't, this condition is really just to do the untwisting. So you get it in general. If you want to have a G being a discrete virtual duality group, virtual Poincaré duality group, you can do that too, and then you'd get suspension by minus the virtual dimension. And if you want to do it with a profinite virtual duality group, the same applies. So that, and if you want to do it with a p-compact group, it's true. I mean, so the different people have proved these results. So the first two things were proved by Dave Benson and me. The third thing on profinite groups was proved by Peter Simons. And then the thing for p-compact groups, and possibly also p-local finite groups, I'm not sure, proved by Natalia Castellana and possibly a collaborator. So there are many other classes of groups other than finite groups where you get something. And I mean, this is part of the, no one has said, we're looking at duality. Gorenstein condition, I'm thinking of it as duality. And you all know the famous title of Basu's paper, The Ubiquity of Gorenstein Rings. They're all over the place, and they've got this duality. And it's also true in this context. Sorry.
Further questions?
It's by degree because A is a graded. Here's the example. So A is graded. So when you take a free resolution, every term is graded, and so yeah. Yes. Well, so yeah, I mean, of course you can draw spectral sequences various ways, but I usually draw it this way. So this would be the 0th local cohomology, the first local cohomology, up to the rth local cohomology. And then if you draw it this way, then your differentials do a sort of Serre pattern. But for group cohomology, I would guess we won't, every group cohomology ring always has depth at least 1. So this is 0. And in the Cohen-Moore-Corley case, of course, these are all 0, and it's only this last column. Right. I mean, I think, you know, for all in the case, in the algebraic case, is exactly the same. I mean, we built it differently. He just took derived function. Sorry.
Do you need R to be commutative?
Oh, okay. I need R to be commutative to do my construction. Yes. And that, I mean, that's a really important point for next time, because I'm going to apply it to rings which are not commutative in the classical sense, but they are commutative enough for me to do this thing.
Any further questions? If not, let's thank the speaker.